Hello everyone. In this video we will continue to examine topic 7.3, the structure of matter, and in particular we will continue to unpack Feynman diagrams. In the last video, we briefly took a look at different types of Feynman diagrams for different interactions, but now we're going to focus in a little bit on other sort of more complex types of interactions, how to produce them, how to show them. The first subset that we're going to take a look at are the electromagnetic or QED interactions. Remember that QED stands for quantum electrodynamics. It was the very first quantum field theory discovered or characterized, and all QED interactions, all electromagnetic interactions, like this one, are actually composed of what are known as vertex interactions. So it's important to recognize that a full interaction, which will need to obey conservation of energy and momentum, among other things, cannot be a single vertex, because they do need to obey conservation of energy, mass, and momentum. However, all of the more complex interactions are built up of a very straightforward set of what are known as vertex interactions, or interactions simply involving sort of three particles in particular. The first we've seen before. So in this interaction, which can be characterized as an electron simply absorbing a photon, an electron comes in from the right, and absorbs a photon coming in from the left, and then moves off in time. So, this photon is coming in from the right. This kind of interaction we've already seen before, and in fact, it is the very interaction in the top right of the Feynman diagram we originally introduced for this topic. Now, take a look at this next one. In this one, a positron absorbs a photon. Now, here's a useful sort of diagrammatic tool. If you want to represent a positron rather than an electron, that is, if you would like to represent any antimatter particle whatsoever, you simply reverse the arrow. Okay, that's it. You reverse the arrow in time. I would not overinterpret this to mean that antimatter particles are reversed in time, although there is some mathematical truth to that. But I wouldn't overinterpret it. Simply recognize that if the arrow is pointing backwards in time, it is an antimatter particle. And in order to obey or sort of draw these Feynman diagrams correctly, you need to reverse the arrow on your antimatter particles. So the positron, which is the antimatter particle of the electron here, is also absorbing a photon. And notice that we got from this first diagram to the second one by reversing the direction of the arrows here. Okay, one thing you will also discover as a consequence of this rule, and the reason we use it, is that if you take a look at a vertex, every vertex will always have one arrow going in and one arrow going out. So you'll see that if a positron is moving forward in time here, okay, absorbs a photon, then the positron is going to leave. Notice that the same thing applies to the electrons right above it. Now, let's take a look at another permutation. So this is another rotation of this set of three things. In this case, you could describe it as an electron emitting a photon. So an electron comes forward, emits a photon, and moves to the left. You can see as above, the arrows point into the vertex and then back out again. Oh, one more thing. Conventionally, the arrows are in the center of the line. So you shouldn't draw them on the end where you normally would. The arrows are used to communicate the important information about whether it is a matter or an antimatter particle, and as a result, need to be drawn in the center rather than at the edge. All right, Now, okay, we're going to rotate one more time, and now we have a very interesting result. Our first sort of discovery, if you will, if you take these interactions seriously. This result, or this vertex interaction, is known as pair production. And what happens is that our photon comes in from the left here, and that energy becomes an outgoing positron and an outgoing electron. Notice that still you have one arrow coming into the vertex and one arrow going out. Notice that this interaction obeys conservation of charge. So before the interaction, it's neutral, and then after the interaction, it's also neutral. And you can see that this involves the straight-up production of two particles here, an electron and a positron from a photon. This occurs, although I will say that this particular vertex interaction cannot occur alone or by itself due to conservation of momentum. As a result, you actually need a couple of interactions to allow for pair production, but in fact, two photons are enough. So if you have two photons coming in, they can interact in a number of vertice interactions to become an outgoing electron and positron. And this happens. A photon with sufficient energy can materialize into an electron or positron and positron pair. Notice you need both. The reverse of that also happens. So if a matter particle and an antimatter particle collide, you get what is known as annihilation, which is a formal term. In this particular vertex interaction, the two particles collide and produce a photon. In sort of real life, in space, you do get pair production, but it is almost always followed by annihilation. Annihilation is also why matter and antimatter need to be kept separate if they're going to be kept existent. So anytime matter gets near its own antimatter particle, notice that by definition, such an interaction will conserve all possible quantum numbers, and as a result, you get annihilation. So that is a common theme in sci-fi, is the use of matter and antimatter to make a bomb or something like that.